Lectures this semester, and I'll post them on YouTube. And I'll put a link to my YouTube channel on Blackboard so that you can find the videos more easily. But I wanted to start by just giving you an overview on what we're going to be trying to pursue this semester, like what the course is about. And you can divide the course into two main sections. There's, at the beginning of the course, a focus on closed conduit flow, meaning water going through pipes generally. And we're going to be trying to find accurate ways to measure the relationship between changes in energy, flow rate, and how much energy we have to put into a system when we want to achieve either a certain pressure at a point or a flow rate between 2 points. And so closed conduit flow is the focus of the first part of the course. And that's also the focus of the project that you'll do this semester. This semester we're going to do a design project where you'll be utilizing some really sophisticated and I think it's fun to use software called Water Gems made by a company called Bentley. They also make MicroStation. It's the same umbrella organization that owns a lot of software. But you'll do a design project that I know some of you have already had some design classes already. For others, it may be the first time you've really done an open-ended engineering design where you start off by evaluating what are the design criteria and what's the need that has to be satisfied. So I really like that design project, and so I'll give that to you about halfway through the semester once we've covered enough of the information related to closed conduit flow that you could make some good headway. The second part of the course answers the question, how does water flow through open channels? And there are some related equations, but distinct, that describes the relationship between depth, slope of a channel, the width of a channel, and the flow rate that's going to occur. And so as you'd expect, the roughness of whether you've got jagged rocks or a smooth sandy channel bottom can have an effect on those things. And so a lot of the equations that we utilize when we're doing closed conduit flow has some sort of a related but slightly different version when we look at open channel flow. And then to a lesser extent we'll also look at things like reservoirs and a few topics that tie into both of these, but I know many of you are also taking hydrology, and so it's kind of a continuum, the range of topics that we address in hydraulics and hydrology. And in hydraulics, what we're doing is we're starting with the given flow rate and trying to figure out how big of a pipe is needed or how big of a channel. Or if you've got a certain pipe that you're trying to analyze that exists, maybe it's already in the ground, you're trying to figure out how big should the pump be in order to get the quantity of water that's needed by people in a certain part of the city. So I think it's a really interesting questions that we're trying to get through this semester in hydraulics. All of you took fluid mechanics from Dr. Yoon, right? Everybody here had Dr. Yoon. And I know he does a really nice job laying the foundation. You know, he taught it also in the past, and I was really happy with what the students knew when they came to hydraulics the following semester. So that's the overview. What we're going to do today is go through some announcements, look over the syllabus, and we'll actually get into the technical material for the first time today. So the number one announcement I'll make is that it's important for you to get the textbook. This isn't a class where you can skip buying the book, but luckily it's relatively affordable. I checked online today and I found on Amazon's marketplace you can get the book for as low as $42 in acceptable condition. The bookstore has it new for $188. I don't think they have access to the same pool of used books that Amazon must, and so it's a little bit cheaper, a lot cheaper on Amazon. So definitely get the book. And part of the reason why is we're just going to scratch the surface on certain topics in the lecture. And you'll have a handful of assignments where it'll ask you a question and it's something I've never told you about. So I think maybe on the first assignment I ask you to evaluate something according to the Morris and Wigert criteria. I'm not going to talk about that in class, but I know you're smart enough to read what it says in the book and answer the question. And that's actually going to be something that will happen really a lot when you graduate and enter the engineering profession, where you'll need to train yourself on what something is, and you'll have to look at how to solve it from previous examples and then implement that for the project you're working on. And you won't maybe have anybody to ask questions about who's done it before. So I'm not saying you can't ask me questions, but I am saying you're going to have a couple of homework problems where there's some little aspect of it that we won't cover in class, and it will be in the book. So you'll need to get the book for that reason, among others. Okay, syllabus. I've handed out the syllabus. Did everybody get a copy of that? Let's just go over some of the greatest hits. And by the way, the syllabus is posted on Blackboard. Let me just show you a couple of things on Blackboard so far. I haven't added everything that I plan to, but I do want to point out that the syllabus is available on Blackboard, and today's notes are posted there. If you like to take notes on top of a PDF, you can do that. But here on the courses page, the syllabus is right in the at the front and center. There's also where I'm going to put the lecture notes, and the first homework assignment is posted there. It's due Wednesday of next week. But all right, so let's just look over a few things related to the syllabus. You can see the course description, our class meeting times. My office hours are Monday and Wednesday from 2 to 5. And I'm happy to talk to you outside of those times, but that's when I'm going to really make an effort to be in my office and try to avoid scheduling other meetings so that I'm available to you. And I looked on, there's a report I can run to see when you have open times. And I think almost everyone in the class is free from 2 to 4. So I'm hoping that that'll be a good time for you to come ask me questions if you've got them. You can also give me a call on the phone, send me an email, and if you've got Microsoft Teams, you can click on this link and it'll initiate a like a video call over Teams. And that can be good if you're working on a spreadsheet or on a software and you're having some kind of a problem that I need to be able to see. It's a lot more efficient to show me what you're hung up on than to like type in text describing it, you know. So feel free to call me on Teams, including outside of my office hours, and if I'm available, I'll go ahead and pick up. So any questions so far about anything related to the course or the syllabus so far? Okay, here's the ISBN for the text, and if you use that, you'll be able to find it available online pretty cheaply. Another thing that you're required to have this semester is access to a Windows computer. So if you love a Mac, that's great. I'm happy for you. But unfortunately, Mac won't run some of the software that we're going to be using this semester unless you have one of the old Intel chips where you could like do boot camp. And I don't know, maybe the new M1 you can have a simulated Windows environment if you use Parallels. But the point is some of the software we're using this semester is PC only. And so if you don't have a Windows laptop, I think they'll let you check them out on a day-by-day basis from the library, or maybe you have friends that have a Windows laptop that you can borrow. But I'm going to give you details on how to download the software that we need well in advance so that you can get that installed on your computer, and then we can actually use it in class and not waste all of the time just troubleshooting installation issues. So I want to let you know in advance about that. If you have any trouble with Blackboard during the semester, the syllabus has links that can take you to that, and here's some details about how to get support from Bentley, which is the company that produces our hydraulic design software. The course outcomes are practiced and assessed in a variety of ways if you care to have that information available. I'm not going to be taking attendance this semester. It is required for you to come to class, but I'm not going to be monitoring or enforce that requirement. And if you happen to miss class, my recommendation is to watch the lecture video that will be posted on YouTube. It's better than nothing, but I don't think it's the same as actually being in class, just because it's harder to pay attention when you don't have the social pressure of everyone else paying attention and the instructor glaring at you if you start playing with your phone. So I'll do my best to help you pay attention by glaring at you if you're playing with your phone this semester. Yeah, so I'm not going to take attendance. I kind of got burned out doing that last semester, and so it'll just be up to you whether you want to learn. Here's how the course is going to be graded. You can see that a pretty good portion of it is homework assignments. Then the midterm exam 1 is a greater proportion of the points than midterm exam 2, simply because we're going to have more class meetings and more material prior to the first exam compared to the second one. The final exam will be comprehensive, so it's important for you to study in such a way that you actually retain the material through the duration of the course. A big part of your grade will be related to the design project, and to help you do that in a systematic way, I'll have draft submissions through the semester where it's not going to all be due at once on the last day of the semester where you've kind of maybe put it off and procrastinated. There's going to be intermediate submissions that a part of that grade is built on what you submit along the way. And we're going to have a couple of very low stakes quizzes this semester. My target is for us to have 3 quizzes. They'll be not necessarily announced in advance. I might or I might not announce them in advance. And they're going to be worth approximately 1% of your grade. If we have 3, it'll just be 1% of your grade. So it's nothing to get worked up about, but it's just a way, for example, if I give you a quiz prior to the first exam, it's a way for you to know whether you actually know things to the level that you ought to before the exam. Homework should be submitted neatly. Typically, if you've done hand work, like writing on paper, what you ought to do is scan it as a PDF, a single PDF that has multiple pages, and upload that to Blackboard. And then that way the grader will be able to give you feedback, not have to switch between a bunch of JPEGs. If you upload JPEGs rather than a PDF, I'll tell the grader not to grade it. The Blackboard is good with some things and bad with others, and for whatever reason it's really bad about quickly displaying and flipping between multiple JPEG files. It's just a real mystery why it struggles with that, but the long and short of it is that you need to submit your homework as a PDF. And so there's a variety of different apps you can use on your phone, like Cam Scanner, or Adobe has an app where you just take a picture and it will assemble a PDF for you that then you can upload that to Blackboard. And when calculating your grade at the end of the semester, I'll drop the 1 lowest homework assignment score. So that, if you miss an assignment because you're busy with other things and you just don't turn it in, then that obviously would be the one that gets dropped. Otherwise, it would just be the lowest of the ones that you did submit. Late work is not accepted unless you have a university excused absence, and you don't get one of those from me. You get your university excused absence from the Office of Student Affairs, and so the link to that form is here. So if you're sick, you don't need to email me. The Office of Student Affairs will let me know when your absence has been excused, and then if you have an excused absence that covers the day that an assignment was submitted, then you can submit a homework assignment late. But other than that, homework is not accepted late. The grader that I have this semester did really well in the course. I think the grader is a really organized individual, and my target is for them to grade your assignments typically within a week of you submitting it. And I hope to do the same thing when it comes to exams, have them back to you within about a week of when you've taken them. I take academic integrity seriously because I think it's the only way that you're going to be able to learn is if you go through the mental effort of struggling with this material. And you're not going to learn as well if you're sitting with a friend and kind of just writing down what they do as they solve the homework assignment. So it can be good to check your work with other people when you're done to make sure that you've understood it, but I suggest it's best if you work independently. And so I have some acceptable behavior and unacceptable behavior when it comes to assignments, and it's okay to talk about the problems and check answers, and if you have a mistake or what you suspect is a mistake on your assignment, it's okay for them to look at what you've done and offer some general suggestions, but it's not okay for somebody to put their homework assignment down in front of you and show you everything, every step by step of what they did, because then that's robbing you of the opportunity to figure it out on your own. And you're just kind of kicking the can down the road of when you're actually going to learn this stuff. And for many of you, hopefully you'll be taking the FE exam in the very near future. And there's a lot of questions related to hydraulics and water resources in the FE exam, so you got to know this stuff. It's also not okay to just give your assignment to someone else or to send them a copy of the PDF, because inevitably they'll be tempted to either copy it directly or be inordinately influenced by how you solved it, and then they wouldn't figure out the method or the procedure on their own. The incoming assignments are going to be screened for inappropriate collaboration, and when I find that two students have collaborated in an inappropriate way, what I do is I give them negative points on the assignment. So you're better off just not submitting something. Like if it's an hour before it's due and you're thinking, oh, should I copy this assignment because I'm going to get a 0 anyway, it's better not to copy it. It's better to have the 0 than to have negative points, which is what you'll earn if you turn in copied work. So any questions about the academic integrity expectations? Okay. There's a whole variety of university policies related to other topics that I'd encourage you once in your life to go through those and familiarize yourself with all of the things that governs our lives here at Marshall. Okay, probably the most important thing in this handout is the schedule. So you can, at a glance, see the topic of every lecture, the due date of every homework assignment, the related textbook material for every section of the course that we're going through. You'll notice, for example, that I already on February 1st have us down for a, is that right? February 1st? That couldn't be right. I think there may be some date mistakes on here. Let's see. Yeah, February 1st is a Thursday. I'm going to have to give you an updated version of this. It's February 2nd is going to be an online class. I'll have to double check this column, but I'll be going down to NCES to help work on the FE exam. I'm a part of the committee that writes the questions for the test, and so that day I won't be available, so we'll have that class meeting just posted exclusively as an online video. So you'll also see on this, it also shows when some of the draft submissions for the design project are due. So it's got both the homework assignments, the design project submissions, and the date and time of our final exam. There are a couple of students here in the classroom that are signed up for a related graduate course. So this class is a mix of students who are taking Civil Engineering 331 and then also Environmental Engineering 670, I think. 671. I don't know. One of the two. I'll provide a different schedule and syllabus for those students. Graduate students have a few extra assignments and some additional readings that they've got to do, but a lot of the content is overlapping, and so many of the lectures are in common. Any questions? No? Did anybody go outside of West Virginia during the vacation between semesters? Who went somewhere far away like Florida or the Bahamas? Florida? Texas? That's great. Where'd you go?
Mexico.
Mexico. You win. Furthest away. What part?
Went to Cozumel and then Costa Maya.
Any kidnappings?
No.
No? That's great. Yeah.
Close though.
Yeah, yeah. Man, I had a pleasant break, but it was boring. I like to go on adventures, you know, like go to a foreign country, run around a mountain, or, I don't know, eat something that scares me, you know, but I just sat around, cleaned my rain gutters, and here we are. All right. Well, with all that done, I mentioned homework 1 is due Wednesday of next week. Let's take a peek at that. Here in the course content, homework assignment 1. It's 10 questions long. only 8 of them are actually like calculation questions. The last 2 are short answer, tell me in your own words kind of a thing. But you can get started on this today. You know, we're going to cover some content today, and I think between a few things we'll talk about and having access to the textbook, you may be able to get a start today, definitely by Wednesday. One thing I wanted to point out is on the homework, it's got the due date listed here before class on Wednesday the 17th. It should be submitted as a single PDF file. Don't upload JPEGs. And then you can upload multiple attempts. And so if you submit the homework assignment and then you keep thinking about it and you realize you did something wrong, you can just upload another file later, and it's the most recent version of what you submit that the grader will evaluate. So I'll set up all of these assignments to have unlimited attempts available. Any questions? All right. So we're going to be covering sections from Chapter 7. So when you get that book, if you haven't already, maybe some of you already have it. Anybody already have the book? A few people. Good, good. Chapter 7 is where we're starting. The first part of the book is mainly fluid mechanics content that you had in Engineering 318. There are a lot of interesting hydraulic structures out there in the world. The Magdeburg Bridge is one of them that just kind of boggles the mind, because we're used to seeing roads that have an overpass, you know, one road going over another, because cars can easily go up a hill and then down a hill. But we're maybe not as accustomed to seeing 2 rivers intersecting each other, well, a river and a canal. The Magdeburg Bridge was built to connect 2 industrial centers that were already connected by water, but it was kind of an indirect route, because there was a connecting canal to the Elbe River, and they had to go all the way downstream and then backtrack to go to this other place. And so the Germans, being efficient like they are, decided it would be more direct to connect these 2 industrial areas with a straight line rather than an indirect route. And so they built this water bridge to connect them. And it was only about $500 million to put this water bridge in, and I assume it's paid for itself. But it's just an illustration of some of the interesting open channel concepts that we'll be looking at this semester. Here's another aquatic related feature. This is in Scotland, I think. It's a boat lift that takes barges and boats just by rotating, lifts it up, and then this continues on to an elevated canal that's at a higher elevation. It's not just in Europe that they've got exciting stuff like that. We've got some pretty interesting water features here in the United States as well. Central control. It seems a little stuffy in here, right? Central control. The Ohio River is navigable mainly because of a series of locks and dams along the river. I know several people in here work at the Huntington District of the Army Corps of Engineers, and so you're more intimately acquainted with all of this than I am. But it's been argued pretty effectively, I think, that a big part of the strength of the United States comes from the fact that there is this really productive and robust agricultural land in the Midwest, which is overlaid with a navigable river network that makes shipping very inexpensive. That there are other countries in the world that have really productive agricultural land, like, for example, in Ukraine. They have a lot of wheat production in Ukraine. But they don't have the same extremely low-cost transportation that we have access to in the United States with barges. Barges can move tons and tons for very little in the way of cost. And in other countries, they have to use trucks or trains. And because those are more expensive, it's kind of a permanent advantage the United States has, where we're just this fortunate of geography with navigable rivers on top of productive agricultural land, and also connecting industrial centers as well. So being able to haul coal to big cities where they've got steel plants is one of the things that helped the United States to develop at the quick pace that it did. In hydraulic engineering, we're going to be analyzing and designing systems that are related to the amount of water, the timing, the distribution. And so in a small scale, that could be something as ordinary as the plumbing through your house and looking at how when water changes direction, there's a loss in energy through the turbulence that's introduced by a bend. And it can be as grand as figuring out the amount of power that's generated in a hydroelectric scenario at a dam. So we'll be looking at water in pipes and channels and reservoirs. And there are a lot of engineering topics that tie into issues that have social and political consequences and economic consequences. So engineers who work on hydraulics sometimes have to acquaint themselves with the decision-making process that takes into account multiple stakeholders and multiple value systems. And so it's never boring when it comes to water issues. They say that a lot of the future wars are going to be fought over access to fresh water because it's going to become increasingly scarce as climate variability increases. And so water is a very interesting topic, and there's something for everybody in hydraulics and water resources. People who are technically oriented and they just want to do calculations and simulations, there's plenty of jobs available in hydraulics and water resources for that. People who are more people-oriented and they want to go to public meetings and help to negotiate the compromises and introduce people to what's happening. That's at the other end of the spectrum from the person who just wants to be in front of the computer all day, but there's plenty of jobs in that realm as well. So there's a lot of variety available within hydraulics. It's not just going to be all a bunch of calculations if you choose to do this for your career. This class is mostly going to be a bunch of calculations, but I don't want to give you the wrong idea that that's all you'd be doing if you pursue a career in hydraulics and water resources. This is a photo that I took when I was working on my PhD at Purdue University. This is a series of pumps that was in Carmel, Indiana, which is a suburb of Indianapolis, a really ritzy suburb that for some reason is drawing from this really hard groundwater. And I was there to do some experiments with the groundwater, which has really a lot of calcium and iron and manganese. But while I was down there, I just kind of marveled at the complexity of the pipe network. This is water that's coming out of sand filters. And if you've taken environmental engineering before, you know that one of the steps that happens in the production of drinking water is that water that's had some coagulant chemicals added to it is filtered through sand in order to get the clay and other colloidal particles removed. But you always have to have redundancy because one of the sand filters may be in a backwash and there may be another one that's getting repaired, and so you have to have the many parallel flow trains through drinking water treatment, and then that makes the pipe networks very complicated to both design and also maintain. So I've always just thought it was kind of an interesting photo to illustrate the complexity of calculating the hydraulic grade line and the energy losses as water goes through such a complex system as this. A lot more simple is open channel flow in some cases. This is a photo that I took back in 2005 when I first moved over to the United Arab Emirates. I was living in a suburb of Dubai for a few years, and on the opposite side of the country, along the Indian Ocean, is a bunch of mountains that when it rains, because these mountains are so rocky, the water just rushes out to the sea. And so they've had to design these really big open channels in an arid environment that it only rains maybe once or twice a year. And you'd think, why would they need any kind of open channel? But it's interesting in a way, the parallels and the differences between the geography there and here in West Virginia. You know, here in West Virginia, we have very steep topography. Like some watersheds have a slope of 50% or even more. But obviously, most of the watersheds here are heavily vegetated. And that helps to absorb and kind of cushion some of the flashy response that we see when there's a storm. But in the UAE, out in the mountains, they don't have any kind of vegetation to smooth out some of the peaks, and so it's a big job figuring out exactly how wide the channel should be to take the stormwater out to the sea. This is a photo that I took, I think maybe 2008 in Northern California. This is Oroville Dam. So it's a human-made reservoir that's got a dam, and the levels here rise and fall quite dramatically. Here's a picture when the water levels are high. Here's a picture when the water levels are low. You know, there's pictures online of boat docks in Northern California where all the boats are just sitting on the mud. And we're seeing increased climate variability, more frequent heavy intensity storms, longer periods of drought, longer periods of really wet weather in some places. And so that puts additional strain on hydraulic designers to make the systems more resilient. We have to consider a wider range of extreme events. So when we're sizing inlets for storm drains, or when we're sizing storm sewers, we have to ask ourselves not what are the climate conditions now, but what are maybe the climate conditions 50 or 100 years in the future likely to be. Because when you put a pipe in the ground and then put a road on top of it, you don't want to dig the pipe up when weather conditions are changing. So you have to think into the future. And that's what I'll ask you to do on the design project this semester, where I give you a map, a scaled map, and I give you some parameters like the population density in the north zone, and I'll tell you how big is a certain hospital outside of the city limits, and I'll give you this characteristics of a cardboard box factory, and you'll go through the process of estimating the amount of water that's going to be demanded in this hypothetical town that you're analyzing. And everyone in the class will have different parameters assigned to them. So one student will have really high population density, another will have medium population density, and there's all these variables that are going to be unique to you, and you're going to have to ask yourself, based on what I'm given and what research I do online about how much water do people use when they're in a hotel, or how much water is required in a residential neighborhood. You're going to go through this process of evaluating what the likely needs are, and then figuring out how big the pipe should be to deliver water to certain junctions in the city. And you're going to go through an optimization process of making one pipe a little bit smaller and seeing if it gives you adequate pressure at that location within a range of allowed bounds. You'll go through and figure out where on this hillside should you locate a reservoir to cause pressurization in the network, and then you're going to go through the juggling process of, if I tell you how much the pipes cost, is it worthwhile to spend a little bit more to take the reservoir up on the hill, because that's going to increase the pipe length, but then the higher the reservoir is on the hill, the bigger the pressure is in the pipe network, and then that would allow you to make smaller pipes throughout the pipe network. And so this is going to be a lot of moving pieces, and that's the essence of design, is iteration, optimization, and trying to find the most cost-effective solution. And luckily, you're not going to be doing these calculations by hand. You'll have some really powerful and easy-to-use software that will allow you to design the network the same way that you would if you were working professionally and had a real-world development that you were designing. So I look forward to introducing that design project to you, because it's been really a great opportunity for learning and growth in past semesters. Okay, so let's talk about flow resistance. When water is flowing, there are forces which resist its movement. Any fluid that has viscosity is going to experience those forces. Here is a heat map that the red is illustrating high velocity, blue is illustrating low velocity. And you'll notice that as water is flowing through this diversion channel, the velocity is the fastest in the center of the channel. So why, anybody willing to speculate why the velocity would be faster in the middle of the channel than close to the banks? What do you think?
Like nice condition.
Yeah. The water that is close to the banks is in contact with a stationary object, like a rock. And it can't slip over that rock with zero friction. The rock is resisting the water's movement. And so if the water is moving downhill, the rock is pushing on the water in the uphill direction. And the same thing is true of flow through a pipe. That water that flows through a pipe is going to have a high velocity in the center of the pipe where it's furthest away from that stationary object that the water's in contact with. But around the edge, like think about a circular pipe, the water that's touching that pipe material is going to be moving at the same velocity as the pipe itself. Like if you really zoom in and get close, the molecules of water that are in contact with the pipe wall have zero velocity. And then the further away you get from that surface that's providing resistance, the higher the water velocity will be. So how much a pipe or a stream material resists flow is a function of the fluid's viscosity. So if we have a pipeline that's carrying pancake syrup, then there's going to be more resistance because there's a higher viscosity for that fluid than there is for water. It's also going to vary depending on the flow conditions. And as the velocity increases, so does the resistance that is imparted by the stationary solid material to the flowing fluid. The uniformity of the conduit. If the conduit is smooth like a drawn plastic or glass, then the water can slip over that with less resistance than if it's a coarse iron or a corrugated steel that has a lot of roughness. So it can also depend on the geometry, whether you have a really narrow channel or a wide channel. And I'm sure that in fluid mechanics you learned about laminar conditions and how we assess whether conditions are laminar or turbulent by calculating, what does RE stand for? Anybody remember? Reynolds number, good. So below 2,000 and we'll have laminar, above 4,000 and we'll have turbulent, and in between, in the middle range, it kind of depends on what direction you're coming to the flow from. You may have laminar flow if you were gradually and calmly increasing the flow velocity after having been in the laminar range. Or in this intermediate zone, you may have turbulent conditions if, for example, if the water's flowing through a pipe at a Reynolds number of 3,000, but you're banging on the pipe with a hammer, that could be enough to disturb the flow and cause it to become turbulent. Does anybody remember the Moody diagram from fluid mechanics? Okay, good. The Moody diagram is probably the simplest way for us to calculate the Darcy-Weisbach friction factor. And there's a variety of formulas that we can use to answer the question, how much energy is being lost when water flows through a pipe? Like if water is flowing from location 1 to location 2, so water is flowing downstream from 1 to 2. If this is horizontal, the pressure is going to be less at location 2 because the water wouldn't be flowing unless there was some reason for it to. So water flows either like downhill, or in a horizontal conduit, water flows from high pressure to low pressure. So P1 is high, P2 is lower. So water's flowing because the pressure downstream is lower. Or, and it's a chicken and an egg thing. You can also think about it this way. You could think that because the water is flowing from 1 to 2, there is less energy at location 2 because of the effect of pipe friction. And so we could think of it as causal or as an effect. But in the end, it doesn't matter. The reason I bring it up is this formula is the most accurate way we have available to estimate how much energy is lost as the water goes downstream. So this Darcy-Weisbach equation says it depends partly on the length of the pipe, so the distance between 2 points, and Darcy-Weisbach equation says it depends partly on the diameter of the pipe. So the diameter of the pipe is a factor. It depends on the velocity of the water. So if we know what's the speed, if the diameter is changing, then V1 and V2 will be equal. But the velocity through the conduit, and then some factor F, a friction factor that's going to take into account both the flow conditions, the material type, a variety of factors. So I wanted to just revisit how we calculate the friction factor F using a Moody diagram. So this is our first example. Let's say that water is flowing 30 meters per minute through a pipe that has a diameter of 0.25 meters, and then the equivalent sand roughness of the pipe is 0.26 millimeters. So some books and formulas use K sub S to talk about equivalent sand roughness. Some use epsilon. It just means, like, if you had a pipe material and you're going to represent how rough that pipe is with an equivalent diameter sand grain, what would be the diameter of that sand grain that has an equivalent roughness to the pipe? So that's what it's talking about. So this is the roughness, I think, of cast iron, 0.26 millimeters. So what is the F value that would apply in a scenario like this? So what we're going to have to know to calculate the Moody diagram is the relative roughness, the Reynolds number, and then once we have those two, we're going to go up and find one of these curves, the point of intersection, and take it to the left side of the diagram. So let me erase this stuff off of the board and kind of set the stage for what we've got. We've got a velocity, it says, of 30 meters per minute is how fast water is traveling through the pipe. Well, to use the Moody diagram and calculate the Reynolds number, we need to know meters per second. So we just divide that by 1 minute is 60 seconds. So we have a flow of 0.5 meters per second. That's the flow velocity. And the K sub S, or the relative sand roughness, is 0.26 millimeters. And the diameter here is 0.25 meters, which is the same as 250 millimeters. And you'll see why in a minute I bothered to make that conversion. Another factor in calculating the Reynolds number, if Reynolds number is most easily calculated by velocity times diameter divided by kinematic viscosity. We could also calculate it in terms of the absolute viscosity, but most of the time I'll use the kinematic viscosity because there's just fewer terms. We don't have to include density in here. So kinematic viscosity of water at typical conditions is 1 times 10 to the minus 6 meters squared per second. So that's at like room temperature. The kinematic viscosity is 1 times 10 to the minus 6. So let's calculate the Reynolds number here. If we have a velocity of 0.5 meters per second and the conduit is 0.25 meters in diameter, and we know that Reynolds number should be unitless. So hopefully all of these units cancel out when I'm putting the kinematic viscosity in the denominator. And multiply all that together, we get a Reynolds number of 1.25 times 10 to the 5th. No units, because meters squared per second in the numerator, meters squared per second in the denominator. So we're definitely turbulent. This isn't laminar flow. But what we've defined here is where on the figure we are according to the horizontal axis. So 1.25 times 10 to the 5th. Here's 1 times 10 to the 5th, 2 times 10 to the 5th, 3 times 10 to the 5th. So this line is 1.5 times 10 to the 5th. This is a logarithmic scale. And so like 1.5 isn't halfway between 1 and 2. Do you notice that it's a little bit to the right? So 1.25 isn't going to be halfway between 1 and 1.5. It'll be a little bit to the right. Just keep that in mind. That's our Reynolds number. Now, relative roughness, the vertical axis, our equivalent sand roughness to diameter ratio is 0.26 millimeters divided by 250 millimeters. So we're saying, what's the ratio of the pipe material's roughness to the pipe diameter? So that is 0.00104. So on the Moody diagram, we have to find where is the curve that is closest to 0.00104. So we're going to be maybe a little bit above this curve because this is 0.002. So we follow this curve and look for the point of intersection with 1.2 times 10 to the fifth. So following this curve, looking for the point of intersection, it's right there. It's almost as though I created this example so that it would be right at that point where it crosses over to have a friction factor of 0.022. So F, in this case, should be 0.022. Because just to revisit, we start with a Reynolds number of 1.25 times 10 to the fifth and going up and looking for where does that intersect with 0.001, and the two come together right there, and then we follow it to the left and we've got the friction factor. And with that friction factor, now if we knew how long the water had to go through that pipe, we could calculate the head loss that occurs between those 2 points. Okay, that's all the time we have for today. Remember, your to-do list is buy the book, review the syllabus, start thinking about the homework assignment. You could definitely answer questions 9 and 10. That's kind of like non-technical questions. And then I'll post the notes on Blackboard. If you want to download the notes for the whole semester, they'll be on Blackboard before Wednesday is my goal. So I'll see you on Wednesday. That's it for today.